Hi, and welcome to this video on solving linear systems by graphing. Okay, so today we're going to talk about solving linear systems by graphing. So when we talk about linear systems, we're talking about linear functions. And we're going to learn how to use the graph to help us find solutions to a system of linear functions. And sometimes you'll see this called a system of linear equations. Okay, so let's first talk about the possible solutions. Okay, so we have a number of different possible solutions, and you may remember this from when we studied equations with variables on both sides. We studied that when we started talking about solving linear equations. But now we're solving a system of linear equations, meaning that we have two or more linear equations and we want to find a solution. Well, remember that the solution is where the linear equations intersect. And so we're going to be dealing with that in this video and in this chapter. Okay, so first of all, we have three types of solutions that we could possibly have. We could have zero solutions, which we call a no solution. We could have one solution, which we call a one solution. Or we could have infinite solutions, which means that we could have infinitely many solutions because the numbers or the points on a line are infinitely many, okay? Also, we're going to learn a little bit about a consistent and inconsistent system. Okay, so this will be new for you, but there's not much to it. Okay, so I'm going to explain that and just kind of what it means. Okay, so what does consistent and inconsistent mean? Well, an inconsistent system is basically one that has no solutions. Okay, so it's inconsistent. There are no solutions to it. It has really no way to actually find a solution to it, so we call that an inconsistent system. Well, that leaves us with a solution that has a system that has at least one solution. We call that a consistent system because it actually has a solution. Okay, and we have two types of consistent systems. Okay, so if a system has exactly one solution, it is said to be independent. Okay, so we call this a consistent independent system. And then a system that has many solutions, we call it a dependent, so consistent dependent system. Okay, so we have three types of systems. It could be inconsistent, meaning that it has no solution, or it could be consistent, meaning that it's either independent or dependent. So if it has one solution, it's independent. If it has more than one solution or many solutions, an infinite number, then it's dependent. Okay, so this means that there are unlimited solutions to satisfy it. Okay, so for that, that's all you really need to know. But the bulk of what we're going to be doing is actually finding a solution and deciding whether the solution that we find actually satisfies both of our equations. So how do we do that? Well, we've learned how to graph lines, so let's look at some examples. I have a system here, okay, and sometimes you'll see a system written this way with a little squiggly around it. So that means I have two equations in a system. That means I'm going to graph both equations or lines on my graph. So let's graph the first one. The first one I have 2x plus 3. So I'm going to start at a y-intercept of 3, so 0, 1, 2, 3, and then I'm going to use my slope to find other points on the graph. Remember, I can go up to right 1, or I can go down to left 1, down to left 1, down to left 1, down to left 1, until I feel like my line is long enough in order to show what it is that I'm trying to show. Okay, so then I have y equals 2x minus 4. So that's a y-intercept of negative 4. 1, 2, 3, 4. So 0, negative 4. And then it actually has the same slope. Well, what did we learn about lines with the same slope in this last unit that we just studied? Well, we learned that they are parallel, right? They are parallel lines. So in this case, both of these lines are parallel, and we know that parallel lines will never intersect, right? So therefore, they can never have a solution. So we can use this little symbol here, a big fat O with a line through it, to say that this system has no solution. Okay, so now let's move on to the next type of system that we have, and we call that one a one solution. So let's see why. Okay, so I have two lines that I'm going to graph. The first is x minus 5. So I'm going to graph my y-intercept of 0, negative 5. 1, 2, 3, 4, 5. And it looks like my slope is 1 to 1. So up one, right one, up one, right one, up one, right one, all the way until my line is off the page. And then I'm going to graph negative 2x plus 1. So in this case, my y-intercept is positive 1, so that's 0, 1, and I'm going to go down to right 1, or I can go up to left 1. But since I'm trying to find the solution to my system, I'm going to keep going towards the other line, right? Because I want to find out where they intersect. So down to right 1. And so what I get is I get two lines that have an intersection point. Well, this particular intersection point here, well, what point is that? Because that point is important. Whatever that point is, that is the solution to my system. So this point here, it looks like it's 1, 2, so positive 2, and down 1, 2, 3, so that's negative 3. So the solution to this system is 2, negative 3. Well, how many solutions does it have? Well, how many intersection points does it have? Well, it looks like it just has one. Therefore, this is a one solution system. Okay? So how do I know that this particular solution here that I found satisfies both equations? Well, I can check it. Remember the old check? Well, that means that you have to plug this point back into both equations to see if it satisfies both equations. Well, how do you know if it satisfies an equation? Well, that means that whatever points you plug in, your equation should be equal on both sides. So let's try that. So let's do the check. So this is the check for the one solution. Okay, so I have y is equal to x minus 5, and the values that I found were y of negative 3 and the x of 2. And so I get negative 3 is equal to 2 minus 5. Well, that's going to leave me with negative 3. So negative 3 equals negative 3, so it checks out. Now let's check the same point in the next equation, because it should satisfy the next equation also, since we know that the x and y are both equal at that particular point. So let's plug that in. Negative 3, and into x I'm going to plug in 2. So in this case, I get 3 is equal to negative 4 plus 1. And so that's negative 3 and negative 3. So even though the process looks a little different for each one, it satisfies both of them. So that means that 2, negative 3 is a good solution. So it is the only solution to my system. Okay, that means no other point can give me a solution, because the point has to satisfy both this line, the first line, and the second line. So both lines have to be satisfied. Okay. All right, so now let's look at one with infinitely many solutions. Okay, so for this one, how could it have infinitely many solutions? What does that mean? And we talked a little bit about that in solving equations with variables on both sides. Well, for this particular problem, I have y is equal to 3x plus 2. That is the first equation. So I'm going to graph that particular line. So 3x plus 2, 1, 2. I have a y-intercept of 0, 2, and a slope of 1, 2, 3, 1, or down 1, 2, 3, left 1. And so I want to fill up my graph to make sure I have enough points. So this line is in black, right? So I'm going to get another color and graph the second line. Well, remember, you can also graph from point slope form, or if it makes you feel more comfortable to go ahead and distribute this out and put it in slope intercept form, that helps. But if you graph from point slope form, you have a point of negative 1, and then your slope, in this case, is 3. So let's look at that. I have a point of negative 1, negative 1. Oh, it looks like that's the point of intersection. Let's find some more points on the line so we can see what it looks like. So I'm going to go up 3, right 1, up 3, right 1, or down 3, left 1. And what do I find? Well, it looks like this line is actually on top of my other line. And it makes sense because they both have a slope of 3. But in this case, if we were to actually work this one out, so if I have y plus 1 is equal to 3 times x plus 1, if I were to actually put this in slope-intercept form, I would find that I have 3x plus 3 is equal to y plus 1. Subtract 1 from each side, and voila, it looks like it's the same equation. So they are the exact same line. So that's y equals 3x plus 2 for both lines. And so they have infinitely many solutions because a line has infinitely many points. And if all of those points intersect each other, because we're talking about two lines that are on top of each other, then of course there are infinitely many solutions to this system. Okay, so the way we say that is infinitely many solutions. Okay, and some people just abbreviate with many solutions, but infinitely many solutions. Okay, does that mean that all points on the graph are a solution? Well, no, because what if I had a point out here? Well, that point is not on either of those lines, so that point can't be a solution. So when it says infinitely many, it's only talking about the infinitely many points that are on both of those lines. Okay, so if it's on one line, then it's on the other line. So therefore, we have infinitely many solutions that are on the line. So it's not all solutions, but it's just infinitely many. There are a lot, okay? I hope this video has helped, and tune into the next video so that you can get some more practice and we can dig more into systems of functions. All right? See you in the next video.